exist in three-dimensional space, so it'll know that exists at whatever three-dimensional coordinates, and then again there. What that allows us to do is it provides an absolute reference for the origin and orientation of any of the captured data. That then allows us to perform something called a direct linear transformation. And essentially that is going to take two of those views, or multiple views. Two tends to be not as good because your triangulations have quite a bit of error in them. After you get 3, 4, 5, you tend to get a little bit better. Typically, these two views are then put together. You are going to triangulate those three-dimensional points. Those three-dimensional points then can be put into a three-dimensional anatomical model for each of the subjects. This is known as what we call a static calibration. Essentially, we put this in before we have any movement going, and then we have them perform movements within that volume. The next is what we call a dynamic calibration. We also perform this over there, and essentially, this presumes that within each of the two-dimensional frames that we're filming all around the movement, that the cameras are going to see different views of the same point. The computer knows exactly how far these markers are apart, and it looks for several cameras that have the same overlapping markers, and then it can calculate three-dimensional space based on that. Essentially, a dynamic calibration algorithm goes through and scales the entire volume. So essentially, this will do this, but it does it in a dynamic form. So it's difficult for me to explain. I would go out to the volume, and you're going to wave this around. And as you're waving it around, it's capturing several frames. I capture generally about 3,000 frames. It takes all of those frames that it's captured while I'm waving it around, and it can calculate exact distances between these markers and the orientation of the wand as I'm waving it, and then it can basically produce a three-dimensional Cartesian grid within the volume that you framed. Okay. This tends to be the gold standard at this point. It's much faster, it's much easier than we've seen with our static calibration. Okay, so that brings me to what we actually use over in our lab. And we call our lab the Biped Lab. It is the first lab in the country to actually do biomechanics and pedagogy research. So we call it Biped. Oh, Biped.
Also, it goes to humans that have 2 legs.
Yeah, well, there's not a lot of quadrupedal humans, so it kind of fits 90% of the population. Okay. So here we see, this is our lab. We have our camera set up here. Right in this one, we're actually modeling a lacrosse stick. After we've modeled the lacrosse stick, we can have somebody actually go out and we can use it for certain things. This is our camera setup. Generally, you try to have your cameras with 30-degree separation. Ours would generally have, if you were having a biomechanics lab, your dream would be to have 12 cameras. Unfortunately, we only have about this much money. So this camera and this camera don't exist. They would make our analysis a little bit better. But that actually provides us a fairly large space. And I'll show you some of the stuff we do over there. This illustrates the marker setup that we have to use to project that stick figure that we had saw in the two-dimensional images. And essentially, it doesn't mark out where each segment is. It uses a 3-marker combination to estimate the joint centers. And here we go. So here we have clusters of markers that actually project the internal structure of the body. And before we have anybody go into the Vicon, we have them do several anthropomorphic measurements. So we measure how wide their knees are, how wide their hips are, how wide their ankles are. And then the computer is able to go through and project where a digital skeleton would exist on this. So this is the raw data that we get. This is from 10 cameras. Each one of those points is representative of each one of these points is actually identified in three-dimensional space and then projected on our screen. The computer then takes those points and then can actually calculate where the three-dimensional skeleton is. Now, we have several models. The first one is Alfred, and we can see right here, that guy right there, that is the segment of the total body center of mass that it has already calculated. This is Victor, and we can see again the total body center of mass has been calculated there, and we see those markers that we had put on him here and the projected skeleton. And this is the guy we call Olaf. And believe it or not, Olaf is the golden child. He is probably going to be the future of all kinematic analysis. Alfred, Victor, and Olaf, those are the three ones that we use over in the lab. Alfred comes from the aerial performance analysis system that was used in the 80s and 90s. It does not project a three-dimensional skeleton. That is one of its drawbacks. It does do three-dimensional analysis, but these points are actually on the outside of the body. So the skeleton gives you a certain amount of kinematic analysis for the person in three dimensions, but it doesn't give you what Victor does. Victor actually will project a three-dimensional skeleton for you and give you a very specific center of mass. Now, Olaf over here, optical flow analysis, he is much more detailed. We'll get into him here in a second. Now, with the Vicon data, this is what we can do. We can get very specific data in all three dimensions for any given point as they move through three-dimensional space. And that right there is we're tracking his arm. This would be his arm in three-dimensional space. This is one that I filmed today, and this is 4 subjects simultaneously within the same volume. Okay? Each subject has 35 markers on them. So this is 140 markers that are being simultaneously filmed from 10 different views. Okay? Just put this in reference. If I had done this with APOS, this would have taken me maybe a week to do the analysis. With Vicon, with the software that we have, this took 10 minutes. Okay? So we see the people. That's actually, from my point of view, that's very awesome. Okay, and we had them do one other thing. And play rehearsal. And this shows you how fragile this is. This shows you how we've tried to push the system to its absolute brink, and you can see it actually did here. It's not projecting the three-dimensional skeleton anymore because it's losing markers. So, and if you think about it, it has 140 points in three-dimensional space that anytime those points go in front of each other, the computer has to determine, okay, this point was moving like this. I need to project that it's still moving like this. Even though this point, he eclipsed it for a fraction of a second, it has to determine, okay, no, it didn't go like this, it went like this, and this marker went like this. And it has to do that out of 10 cameras simultaneously, okay? There's a reason the software for this costs $10,000, okay?
Haven't you used something called a Colloquium filter for these things?
Yes, actually they use a second order Butterworth filter, and it actually it fills in gaps, and there's a few different things that they have to do because you don't get them. I'm only filming at 100 hertz, which is actually fairly slow, and even at only 100 hertz, you're missing them. Okay, but it can project the empty volume, so it will actually go ahead and put them there. Okay, so. The big thing about this is that APOS and Vicon, they are extremely accurate. Vicon, if you ever go to any motion analysis, new motion analysis system, Vicon is always used as the criterion measure. Okay? Vicon is the gold standard. In the Vicon system, what we just did, that is what you always see with the video games. You always see them in motion pictures. Those are what they use, but they use a lot more cameras. We only have 10, they have way more cameras. They'll have an entire wall of cameras. Okay, actually they have 4 walls, and they'll have a very big volume of space. My lab is probably the size of this room. They may have a lab or a set that is 4 to 8 times as big as this. They'll be shooting across enormous distances. And my markers are passive markers. So essentially we're throwing that infrared light, those are bouncing back to the cameras. They'll use active markers. So they'll have, instead of reflective light, they'll actually, at the origin, they'll have an LED that'll beam it back.
And that takes care of the ambiguity problem, because they can modulate the light.
Exactly. So that is that's kind of the edge of where we are with that. Now, that is the good thing and the bad thing for my research. My research, even though we want it to be extraordinarily accurate, it is very difficult to go out and collect field data for this. I can't necessarily bring 30 students into the biped lab and have them do a class. First of all, I don't have the volume for it. And second of all, it's so intrusive that anything that I'm trying to look at is going to be obscured by that. And so that really doesn't allow me much room. The big thing that is coming along is what we call optical flow analysis. And the guy that I'm working with, Dr. Adriano Barbosa, down in Brazil, he's actually developed a technique for optical flow analysis. And optical flow analysis is very general. We see this all the time. Traffic flow patterns, facial recognition, all of these things work off of optical flow analysis. He's actually just made a very easy application called Flow Analyzer. And it gives you very specific data, and we'll kind of go over that here in a second. The big thing about this is that it's field deployable, it's non-invasive, and it provides very segmented data, so you can pull out what data that you need. It's another thing with Vicon and or APOS. It provides you so much data that you kind of get lost in the weeds. With optical flow analysis, you can kind of pare it down a little bit. And the other thing that Dr. Barbosa has done is he's actually introduced an algorithm for instantaneous correlational analysis between signals, and we'll show exactly what that means here. Okay, so the first one, this is optical